So, in the last few classes we had discussed about variety of techniques of designing multipliers. I just want to remind you that a multiplier is nothing but a voltage controlled amplifier, which can also be designed by introducing MOSFET as a resistor, okay, determining the gain of the stage. We had discussed earlier how MOSFET in the triode region can be used as a linear resistor. Okay. So, we will therefore, whenever we would like to design multipliers, can also take recourse to this technique of designing multipliers. I just want to mention one important technique of multiplication which uses a very novel method for the purpose of multiplication. Let us consider this. I am using FET as a voltage dependent resistor. Let us say we can put the linearizing blocks here as we had discussed earlier, so that it is a linear voltage dependent resistor. This we had seen earlier, right, because the characteristic, let us remind you, for this FET in the triode region, ID is equal to 2k times VGS minus VT into VDS minus VDS squared by 2. If I now make this as the control voltage, then we know that this is equal to 2k into Vc plus VDS by 2. This voltage is, okay, Vc plus VDS, okay, by 2, okay, minus Vt into VDS minus VDS squared by 2. So, you can see how nicely it gets linearized. We also have found out ways and means of doing this without the help of resistors also, right. So, in any case, this demonstrates a particular method of making the FET linear, okay, to VDS. So, we get delta ID by delta VDS, which is same as here ID by VDS equal to 1 over 2k into Vc by 2 minus Vt, right, or the FET resistance R, okay, RDS is going to be this is going to be just this 2k into Vc by 2 minus Vt, okay, or R is equal to 1 over this. K times Vc minus 2Vt, right. So, how do I establish this resistance that I want to be simulated? That can be done by feedback. Now, what I do is put a resistance here, okay. I make this R let us say naught, reference resistance, okay. Apply a voltage, let us say V here, okay, and or minus V here and V here, okay. So, this is Vi, I put minus Vi here, okay. Then what happens here? This resistance has to automatically adjust itself because of the negative feedback such that this current which is V I by R naught is same as this current. That means, this R ds now is going to be automatically adjusted to be equal to R naught. Is this clear? So, this is a negative feedback circuit which will adjust the FET at all times irrespective of its value of K and V t. That means, even if K and V t were dependent upon temperature, this will see to it, this control circuit will see to it that FET resistance is exactly adjusted to R naught at all times. That means, now you have got a perfectly temperature compensated FET resistance, okay, which remains absolutely constant as this fixed value of resistance. Is this clear or not? Now, this is, you call this as a master, okay, we call this master. Okay. Then this master says, I will make sure that you FET, okay, behave yourself properly, so that the resistance value you simulate is constant. Now, once it is made sure, then I can use this, okay, control voltage, same control voltage for all the slaves, okay. FETs which are exactly identical and the circuit, okay, which is exactly identical, okay. These are all slaves, any number you can have, any number of such slaves you can have, all of which get the same control voltage. So, then what happens? And you can independently feed any voltage here, let us call this as V x, okay, and put a negative feedback resistance. So, that this is nothing but an amplifier, inverting amplifier designed using the FET resistance, which has been made to be constant by another negative feedback circuit, independent negative feedback circuit. So, it will remain constant forever, right. Let us therefore have this as, let us say, R feedback, and this resistance that it is going to simulate is going to be how much? R naught. So, the gain of this is minus R f divided by R naught, okay, into V x. And R naught itself is what? RDS, right. R naught itself is nothing but RDS, please remember. This has been made equal. So, let us see what this R naught is. This R naught is, okay, determined by in fact the voltage V I. In fact, I do not have to make this, okay, and this same. Now, this is understood, is not it? So, what I will do is I will keep this as, okay, let us say V r and keep this as V y. Let us see what happens. Now, we know that this is always correct. RDS of this is same as RDS of this. Earlier, when I had these two same, RDS was same as R naught. Okay. Now, I can write down the equation here. V r divided by R naught is the current drawn, that should be same as equal to V y is positive, V r is positive if it is, okay, V y divided by RDS. It is necessary that Vy can only take on a polarity, the positive polarity in this case, if this is my negative. If this is positive, okay, this has to be negative. This is the requirement. Under this situation, Vr by R naught is equal to Vy by RDS, or this can be written as RDS, you replace RDS is equal to, okay, Vy, what is it, Vr by R naught. So, if you now replace this Rf divided by RDS, which is Vy, okay, into Vr, okay, by R naught into Vx. This becomes a divider in this case. You want to make a multiplier out of it, what do you do? Interchange Vr and Vy, right. If you interchange Vr and Vi, this you make as a reference voltage, okay. This you make it as, okay, variable voltage, then you get a multiplier. So, you can design either a multiplier or a divider simply by using this principle of master slave concept, which is similar to what? Current mirror, right. Current mirror, we had a transistor which was connected as a diode. So, that is a feedback structure which was learning to develop a voltage required to pass a current, and this voltage was used, okay, to bias all the other transistors at the same current. Okay. So, same thing is used here in the design of a FET multiplier. In this, it is not necessary to use voltage ampere characteristics of the FET. Okay. Volt ampere characteristic of the FET is of no consequence, strictly speaking, right. This relationship of the resistance being valid, okay, the equal resistance being valid at all times is true irrespective of the volt ampere characteristics. The only thing is here, right, I am assuming that this current, okay, is the current that is passing through this, and that current is determined this divided by that. In that assumption, I am considering that the FET is linear. Okay. Is this clear? Okay. So, this is another technique of designing multipliers, particularly this technique is very popular in regular laboratories, where you can use two matched FETs to design a fairly good multiplier. This is not 4 quadrant, what is this? This is 2 quadrant, because Vy, Vx can take on both polarities, Vy can take on only one polarity. Okay. Now, we will see another application of this multiplier in what is called a very important block, that is universal active filter block. Universal active filter blocks are available by themselves as ICs, and these are nowadays being used as VLSI subcells in realizing higher order filters, analog filters. So, this itself can become a subcell of a very large scale integrated circuit, and therefore, we would like to have some control over these filter parameters. Let us therefore quickly analyze this filter, which you people have already learnt in some of your undergraduate lessons. Let us see if Vi is the input applied here, we can see that this output we will call it as V naught 1. Let us express everything in terms of Vi and V naught 1. So, let us say this is V naught 1, and therefore, this output is V naught 1 divided by SCR, right, with a negative sign, and this output is minus V naught becomes plus V naught 1 by SCR square, and here we have minus V naught 1 by SCR and Vi. So, this V naught 1 by SCR will appear in this case as alpha times plus alpha times V naught 1 by SCR minus Vi into beta, right. So, that is as far as this is concerned. Now, therefore, V naught 1 has output resulting due to these two inputs. So, V naught 1 is going to be equal to, let us say, this will appear as an inverting thing, V naught 1 is minus V naught 1 by SCR square and then minus of this. So, we have quickly seen how this can be simply analyzed, and we get V naught 1 divided by Vi from that equal to beta into 1 plus alpha by SCR plus 1 by SCR whole square, or SCR whole squared beta divided by SCR whole squared alpha SCR plus 1, which according to us can be written as S by omega naught squared, S by omega naught squared plus S by omega naught cube plus 1, wherein omega naught is equal to by comparison 1 over CR, right, and Q equal to 1 over alpha, and obviously here we have beta as beta coming into picture in the gain of the stage, right. So, this is what is called what output? High pass output. If you take the output here, this is therefore high pass. That high pass output into 1 over SCR or omega naught over S minus, which will give you band pass. So, V naught 2 over Vi is nothing but minus S by omega naught beta divided by the same denominator, which is band pass. So, this output is band pass, and again if you integrate this you will get low pass, which is V naught 3, this will be V naught 2, this will be V naught 3. So, V naught 3 by Vi, which is again minus beta divided by the same denominator, which is low pass. That is why there is some universal nature about it, because band pass, high pass, low pass, if you can add or subtract suitably, you can get any second order system. Any second order system block can be got by adding suitably or subtracting suitably these outputs. Therefore, you might need one more op amp for doing this. If you have here an op amp, this output, if you say I would like you to do this work separately, this is going to be band stop output. So, please do this. It is nothing but alpha times V naught 1 by SCR minus Vi beta. It will be nothing but band stop output. Please do this as a homework problem. Show that the output here is a nice band stop output. So, that is why this circuit is very important, because we can just use it for even biomedical application where you want an ECG waveform, okay, which is coming here with which contains lot of your 50 hertz, so called 50 hertz. Okay. Output of this is going to be the same ECG waveform, okay, devoid of the 50 hertz. Okay. So, this is a nice setup for that kind of filtering in biomedical applications. So, let us now see how this can be converted into voltage control filter. So, we can do this very simply by replacing this integrator and this integrator, because here RC time constant means, okay, the 1 over frequency, okay, omega is equal to 1 over RC. So, if I make both these resistances depend upon a voltage, that means if this is made voltage controlled, or if I put a multiplier here, it becomes voltage controlled filter, right. Instead of that, I can just say that it can be made using a FET here and using a FET here, right. If I use this kind of arrangement, it is not linearized. If you want to linearize that, you can do it by putting resistors yes, okay. So, R dash, let us to distinguish from this resistance, R dash, linearizing resistors, and control voltage is connected here. Now, this will be nothing but same day omega naught equal to 1 over C R ds, okay. Q remains the same as 1 over alpha undisturbed, okay, and therefore, and the gain also remains undisturbed, okay. So, you are now able to change omega naught dependent upon RDS. RDS is, we already know how much RDS is equal to 1 over, okay, 2k or k into Vc minus 2Vt. So, using these FETs which we had linearized, we can make this particular filter voltage controlled filter. Is this clear? So, this works beautifully, okay, as long as the resistance of the FET can be varied from a certain value, let us say Vc1 to some Vc2, depending upon, okay, the current that you are permitted to have through the FET, that is all, okay, over this range. Now, this linear voltage controlled filter can be tuned based on this control voltage. For example, let us take the same example. If it is some specific frequency you want to get rid of, so you can make Q fairly high, let us say 100 or so. Therefore, you can now obtain a characteristic here, if you take the output at this point, where the output is going to have a notch at omega naught, which can be varied. Okay. So, you can get rid of the unwanted frequency. Another application for such a thing is, you have a given waveform which is periodic, and you want to find out the harmonic content in the given waveform. So, you can put a notch at the fundamental and measure the power at the rest of the output. Okay. So, that will give you the harmonic content, okay, of the given waveform. Or if you take the band pass output, okay, you can find out the fundamental or the harmonics So, it can become a spectrum analyzer. Okay. So, it can be used as a harmonic analyzer or as a spectrum analyzer, the sweep voltage being given as V c. Okay. So, it has considerable amount of application in signal processing. Now, I want to make this filter self tuned. What does it mean? I am feeding a certain frequency here, let us say 50 hertz. Then I want it to tune itself to 50 hertz. If I change this frequency to 200 hertz, it must go to its center frequency should go to 200, or its pole frequency should go to 200 hertz, if it is band pass or notch or whatever it is, right. So, I want the pole frequency to be now tuned automatically. Let us give this problem as a problem of tuning by a student. This is given to you in the lab. You are given this frequency as the incoming frequency, let us say reference frequency. Then you are asked to tune this filter to the incoming frequency. So, obviously, we will change the V c. Right. We might take any of the outputs for finding out whether it is tuned to the incoming frequency or not. Now, in this particular case, suppose you take the band pass output, how will you know that it is tuned? This is the same question, right, that I had asked the PGs last time. I am taking the band pass output for observation output. So, how will you know that it is tuned to the incoming frequency, let us say 50 hertz or 100 hertz? How will you know? Gain will be? No, not necessarily, right. Gain is determined by beta, right. What is the band pass output characteristic? It will have a peak, but this is what is again always used as the wrong information. Peak means what? Mathematically, the magnitude does not vary with respect to frequency, band pass. Whereas, in order to find out whether around that frequency it is tuned or not, something has to vary much large by great extent. So, this is something that even though is visible for a high Q circuit, this is visible as a technique of tuning. This is the wrong method of tuning, whereas we should make use of another parameter, that is phase variation with respect to frequency. How does phase vary with respect to frequency for a band pass? Let us have this characteristics S by omega naught minus beta S by omega naught squared S by omega naught q plus 1. Phase of this is 90 degrees, numerator. Denominator is the one which causes phase variation with respect to frequency, which is nothing but tan inverse omega by omega naught q divided by 1 minus omega by omega naught square, right. That is the phase variation with respect to frequency, right. And if you maximize this, find out delta phi by delta omega. Please do this as a homework problem, and you will find that this will be maximum at omega equal to omega naught, and is going to be equal to how much? See, it is at omega naught, phase shift is, just look at this, S get cancelled, right, this is going. So, it is 0 phase, right, phase shift is 0 or 180 degrees, right, in this case it is 180 degrees. Phase shift at the resonant frequency is 0, that is known to you, for the band pass output 0 or 180 degrees. But phase variation you can see is dependent upon, is directly proportional to Q. I would like you to evaluate this exact value. What is delta phi by delta omega at omega equal to omega naught? Please evaluate this as a homework problem and see for yourself that it is directly proportional to Q of the circuit. That means, if I plot the phase variation, initially the phase shift is starting at, let us say, minus 90 or whatever it is. So, going over to 0, going to plus 90, right, and it is this slope that we are talking of, which is delta phi by delta omega, and that is highest at omega equal to omega naught, right, and is dependent upon Q. Higher the Q, steeper this is going to be, and therefore, if you want to check whether you have exactly located your center frequency or not, you have to find out the phase difference, because the phase is going to vary the maximum around that frequency, whereas the magnitude is not going to vary at all by definition, because it is flat, because it is the maximum, right. Phase variation is maximum. So, please remember that in any circuit, therefore, if you want to adjust the frequency exactly, you must use always the phase variation with respect to frequency, not the magnitude. So, phase detector is invariably used, not magnitude detector. So, that means I need a phase detector. Let us now therefore use a phase detector, but then the phase detector that we used was capable of detecting only phase not from 0, but from 90 degrees. Do you understand this? Right? We said our phase detector that we had used earlier, multiplier type of phase detector or AND or gate phase detector, was not capable of detecting phase, that is leading and lagging phase, if it is starting from 0. We had to have a quiescent phase shift of 90 degrees. That means, it is advisable not to use the output of the band pass, but we must use additional phase shift, which is already available to us. Therefore, if we use additional phase shift of 90 degrees, that means either low pass or band pass in this structure. We can use it in combination with our phase detector that we have learnt to find out how exactly I have to shift the frequency in order to tune it exactly to the incoming frequency. Is this clear? So, we must, in a given case, if you have only band pass output available, you must shift it by a additional phase of 90 degrees or put an integrator or a differentiator. But in a given circuit, if you have low pass and high pass available or high pass available, then you can take the output from these. So, let us therefore take the output from this, let us say high pass, and the input, and put a phase detector and how is the phase detector simply designed? Let us say we put a multiplier, right, linear phase detector I am putting. We do not have to put a linear phase detector, but right, for analysis, simple analysis it is. So, we have put a linear phase detector now. It will become a phase detector primarily when I take the DC out of this right. So, average, this average will tell me whether it is tuned to. So, since I have taken the high pass output corresponds to plus s squared by omega naught squared, and you can see if it is exactly tuned to omega naught, omega is same as omega naught, incoming frequency omega is same as omega naught, this will get cancelled and I will get a phase shift of how much 90 degrees, okay, exactly at that frequency. When there is phase shift of 90 degrees, what will be the output? This you have already noted earlier, we have worked it out for this. Okay. When the phase shift is 90 degrees, the output is going to be, look at it, 0, right. When the phase shift is 90 degrees for this circuit, the output is going to be 0, right. Its phase characteristic, if you remember, right, it was going like this. Am I correct? Okay. From let us say plus Vs to or plus 10 volts to minus 10 volts to 0, right. This was the phase characteristics with respect to, let us say this is pi, this is pi by 2, 0. Okay. So, we can find out whether it is tuned to the incoming frequency or not moment we get a 0 average voltage at this point. Is this understood? Now, how do I therefore make sure that this is going to be the case automatically? So, I put a comparator here, okay, and connect this up. This is the VC. This is an automatic, okay, frequency locking scheme, right. It gets automatically self tuned, right. This voltage has to automatically become equal to 0. If this is a negative feedback system, since I am using an op amp here, this output should adjust itself so that this voltage and this voltage become one and the same. If it is a negative feedback system, that you have to make sure. So, of course, the proper polarity has to be put here to see that, okay, it is a negative feedback system. Now, I would like you to go through this entire scheme. We will do it once again later and make sure that this particular scheme functions as a negative feedback structure. Right. What does it mean? When this is at omega equal to omega r, if the original frequency to which it was tuned was less than omega r, now the feedback should be such that it should be brought towards omega r, that is negative feedback system. So, let us see, for this particular case I am using a n channel MOSFET. Now, we have some time to find out whether it is negative feedback or not. We will do it now itself. Now, I have not marked the polarity of the last amplifier, that I will change depending upon whether it is going to be negative feedback. Okay. So, let us see. I know now that this particular thing omega r, let us say this is the omega r, this is the incoming reference frequency. So, I should know how phase varies for this particular thing with reference to omega r. So, you just can put this as s is equal to j omega and omega equal to omega r. So, as far as numerator is concerned, we are not bothered. As far as denominator is concerned, okay, we know that as omega r is very low, as omega r is very low, okay, what is the phase shift? This quantity is going to be very low. The phase shift is determined primarily by this that is essentially it is minus 90 degrees. Okay. So, as that is from the denominator. Okay. Numerator itself is going to give you how much? A phase shift of 180 degrees. Okay. So, that you can ignore, right. So, afterwards as omega comes close to omega naught, okay, this quantity vanishes, it becomes exactly equal to 90 degrees. Okay. As this goes very omega goes very high, you can see that the phase shift becomes, this becomes negligible, this becomes dominant, this negative quantity. Okay. So, it goes to 180 degrees, right. Is this clear? As far as the numerator is concerned, this magnitude itself is going to, okay, close to 0, okay, when S is equal to 0. Okay. So, the phase variation of this, if you plot, okay, we have already plotted it here. So, it is going to vary in this fashion, right. This is going to be pi by 2. Okay. The initial phase variation is primarily determined by, okay, the numerator rather than the denominator, okay, because S is j omega r and omega r is very small, right. So, it is starting with a phase of let us say 180 degree, okay, and going to minus 90 degrees, okay, going to 0 degrees like this. Okay. So, whether it is minus or plus, it does not make any difference, 180, 90, 0, that is how it is changing. This nature of variation you should know. So, if this is the nature of variation at this is omega equal to omega r equal to omega naught, the phase shift is this, right. So, let us say omega r is less than omega naught, omega r is less than omega naught, then the phase shift is closer to 180 degrees. Okay. This is important, it is changing from higher phase shift to this. Okay. Now, as far as the phase detector is concerned, if the phase shift is closer to 180 degrees, we have started with omega r less than omega naught, okay, omega r somewhere here in this region, right. When the phase shift is greater than pi by 2, you are getting a negative value. Okay. So, this voltage is negative. If this is negative, let us put this as negative just for argument, then this would have gone to more positive voltage, more positive or less negative, more positive here. More positive means, okay, the resistance is going to decrease. This is n channel. So, the resistance is going to decrease. If the resistance decreases, the frequency is going to increase, and we want this omega r to, omega r is remaining same, omega naught is going to increase, right. So, this is positive feedback. Yes. Is this clear? This positive feedback. In order to make it negative feedback, what should we do? We can change any one of the things. Either we make this, okay, because I would like to change this rather than anything else. Instead of n channel, I make it p channel and retain this as minus, because I would like to not use large capacitors here. Instead, I would like to use Miller effect and make this an integrator. So, this is what is called a self-tuned filter, okay, which is going to now work satisfactorily. What does it mean? Where is it used? This is used when the signal to noise ratio is very high, noise, that is signal is buried in noise. But we know that the signal is almost a single frequency, that is okay, the bandwidth of the signal required is very small. Therefore, I make a very high Q self tuned filter, okay, and let it get tuned to the incoming signal, then it will eliminate all the other noise around it if it gets locked onto the signal, right. So, this is one way of searching whether there is a signal anywhere in space. Okay. We do not know who is sending our information, okay, from in space, but we know that this information is a band limited highly narrow band signal. So, you can keep scanning, okay, the entire range of frequencies using this kind of self tuned filter. What you do is you can skip ranges by making VC get disconnected and making it a sawtooth and search in different ranges of frequency and see whether anything is getting locked. Okay. Once it is locked, it will keep on tracking. Okay. So, this is really used in space applications, okay, for finding out signals from unidentified sources, okay, and they just keep recording it for years and years to see whether there is any intelligible information coming from these sources. Okay. So, in such amplifiers these self tuned filters are used. Okay. Thank you.